Let's continue our discussion on ensembling, learning, and random forests. Specifically, we want to discuss gradient boosting. So here, as a review, you know that bagging is drawing from different samples, and boosting is trying to use weak learners to build a forward stage-wise additive model to help to improve based on the weak learners' weakness, and with hope that we are able to come back with a better learning process, and also combine different learning predictors to come back with a better model. And then this is the definition of boosting. It would be combine several weak learners into a strong learner. And then as an example, to specifically in ds630, it leverages by adjusting the weights so that you can improve upon the previous iteration. However, here what we want to discuss are gradient boosting. It's a very popular boosting algorithm, and just like ds630, gradient boosting works by sequentially adding predictors to an ensemble, each one correcting its predecessor. However, instead of tweaking the instance weights at every iteration like ds630 does, this method tries to fit the new predictor to the residual errors made by the previous predictor. So it's not adjusting the weights of the observation, but it's trying to fit the prediction error coming back from the previous predictor or previous model, with the hope that it can improve upon the previous predictor's error. So let's look at this as an example. So a simple decision tree regressor have max steps equal to 2, and then we feed the data tree 1, regression 1, and then what we do is we use tree underscore reg1 dot predict x so that we know the predicted y. We use actual y minus a predicted y from the first model, so that would be y2, which is the residual error made by the first predictor. And then we define the second tree underscore reg2 and fit x with y2 instead. So fitting the residual errors that made by the first predictor. Now we use the same thing so that we would be able to come back with the residual error made by the second predictor. So y2 is the original y for the second predictor, and then we predict on x using second model tree underscore reg2. So we'll come back with y3 and use that y3 to build another model. Now we have 3 different trees: tree underscore reg1, tree underscore reg2, and tree underscore reg3. We have an ensemble containing all 3 trees. It can make predictions on new instance simply by adding up the predictions of all the 3 trees. So this is called gradient boosting. Of course, by no means that with only 3 trees it's going to do a good job. So it's really just for illustration purposes. So yeah, y prediction would be equal to summation of tree that predict x new for all the trees. For the tree, it's actually in tree underscore reg1, tree underscore reg2, and tree underscore reg3. So this is a gradient boosting example. You could also leverage this called gradient boosting regressor that's in scikit-learn.ensemble. And then in this gradient boosting regressor function, you could pass in max steps equal to 2 and n estimators equal to 3 decision trees, and the learning rate equal to 1.0. And then you can use that to fit this gbrt.fit on the x and y. Let's look at this example to look at how exactly it's working. So in this graph, on the left-hand side, if you look at the top left, it is trained normally. And what it does is using x1 being x1 and then the corresponding y. And you come back with a regression model, decision tree regression model, right? With this regression model, apparently each observation has a residual error because this is prediction versus this actual value. It's if you look at specifically looking at this particular observation that I have here, it's probably using the, so it's would be something, let's use this one, it's actually easier to understand. It's using actual minus predicted value, and then you come back with some sort of negative value, right? Negative point, close to negative 0.2. So that would be somewhere here. This is your residual error. So in other words, you calculate the residuals, comes back with this model, and then you have all the residual numbers right there, and then build a new model, which is the second model, that y-axis is y minus using h1 to corresponding predicted value of based on h1. And then this model is our h2. This decision tree regression model is our h2. And the next model is calculate the residuals based on this model and use that as my dependent variable to build the third decision tree. And then your ensemble prediction would be on the right-hand side of this chart. And then the first one would be doesn't make any change just because it's just one model so far, right? And then the second model it does is it's addition of h1x1 plus h2x1. Specifically, let's use some examples to show you. For example, here, somewhere here around 0, what happens is the first model is predicting somewhere around 0.17. Let's put it that way, right? 0.17. And then for the second component, h2x1 is actually predicting somewhere around negative 0.1. Less than, it's probably a little bit less than negative 0.1. So that if you add those two together, 0.1 something more than 0.1 plus this negative 0.1, it should be close to 0. Apparently, it's a little bit larger than 0. So you can see anything that's between negative 0.2 to 0.2 is kind of in the same range just because these two add up. However, anything that's less than negative 0.2, originally your prediction is this, but now your prediction is kind of going up a little bit. So it should be a little bit better. Now it's this new prediction. Same thing for other regions as well. And then if you continue to add the third component, this would be your final model in terms of your ensemble prediction. Apparently, if you look at this model versus the first model, it's doing much better job. Okay, this is called gradient boosting. And then in gradient boosting, there's a hyperparameter. It's called learning rate. What it does is scales the contribution of each tree. If you set it to a low value, for example, as 0.1, you just have not a lot of contribution for each tree. And then you need more trees in ensemble to fit the training data set. And then good news is actually if it's small, the predictions will usually generalize a little bit better. So this is a regularization technique, something called shrinkage. So learning rate set into a smaller value, and you need more trees in the ensemble to fit the training set. And this whole process is called shrinkage. And here is just an example. If you look at what's on the left-hand side, for the gradient boosting trees, and then on the left-hand side, it doesn't have enough predictors. You have a high learning rate, and then you only have 3 trees that can help you. And on the right-hand side, you have a learning rate of 0.1, but it has 200 trees. Apparently, in this example, it's actually too many. So the question becomes, what would be the best optimal number of estimators or number of trees that we could have in a gradient boosting algorithm scenario? Now we want to figure out what would be the optimal number of trees. So a simple way to implement this is to use staged predict method. It returns an iterator over the predictions made by the ensemble at each stage of training with 1 tree, 2 trees, etc., etc. So you can just take a look at this. What you do is, of course, you have regular train test split, and then you have gradient boosting regressor, max steps equal to 2, and estimators equal to 120. And then you use that GBRT.fit to fit this y versus x. And then you have errors to use mean squared error of y value and y predict. For y predict in GBRT staged predict x file. So use this method to retrieve the staged prediction of all different sizes of the trees. And after that, you figure out which one actually give you the minimized error to decide best number of estimators. And then you use that best number of estimators that you come back previously to run your gradient boosting regressor, so that would be your final best optimal number of trees. This is an illustration of what that means. So what you do is you look at this, the number of trees versus y-axis is a validation error, and then turns out to be around 56 would be the minimum of validation errors. And then you use that 56 pass in the second stage, and then run the best model. The best model turns out to be 56 trees, and then the prediction look like this for this particular case. That's a gradient boosting algorithm in scikit-learn. One more thing that we want to discuss here is something called XGBoost. So it's an optimized implementation of gradient boosting in Python library. It's called XGBoost, which stands for Extreme Gradient Boosting. And then, in fact, actually, XGBoost is often an important component of the winning entrance in machine learning and computations. XGBoost API is quite similar to scikit-learn's. And then here, just give you some example how you can leverage SG boost regressor. It also have other nice features such as automatically taking care of early stopping, and here, for example, just show you early stopping rounds equal to 2, so that you can leverage XGBoost in the Python library. It's a separate library from scikit-learn, but it's definitely something that you should check it out and explore. Okay, I'll stop here for gradient boosting. Thank you.